So essentially what quantum is trying to achieve is to take all of the normal processes that you would find in a pathology lab and put it into a handheld device. So we will cover cell lysis, extraction, amplification, detection, integration, and we probably won't get time for the sequencing part of it, but essentially being able to put all of these processes into a single device. Okay, so this is a little movie that helps explain, for those who aren't scientifically gifted, the process that we're doing. Now, in the terms of open innovation, this is actually done by Ian, who at the time was working in Northumbria University. So essentially this is what we're doing. So you take a pinprick of blood, generally about 15 microliters, and it goes into a cartridge. The cartridge is essentially then inserted into a handheld device, and from there we go. So the technologies are fairly simple. We lyse the cells, and the cells will be a mixture of lots of DNA, genomic DNA, viral DNA, bacterial DNA, and we essentially just extract the DNA out of this. From there, we go into a PCR stage. Now this takes a little bit of time, but PCR is essentially DNA photocopying, and what you do is you heat it up, which is why it turns red, and then slowly you amplify your DNA. The two daughter strands are then partnered, if you like, and then we'll go through again, and essentially you go from 2 copies to 4 copies to 8 to 16 to 32 to 64, 1 to 8, and it goes through like that. So depending on how much DNA you start with, you end up with an awful lot. Each cycle of heating and cooling doubles the amount of DNA you have, and this is forensic work, bread and butter, and Nobel Prize winning science. Then we move on to an area of work which we work with Harvard and Yale universities on this, and it's nanowire technologies. They act as field effect transistors, so they sense what's in their local environment, and you're able to partner DNA and look through a diagnosis from there. And if we move on, so open innovation. We work with an awful lot of people. The hardest thing about this talk was going through all of the NDAs to make sure that I wasn't breaking any NDAs by talking about them. But you know, there's a range of different institutes and universities and hospitals and small companies and large companies, and most of the large companies don't want me to talk about working with them, so there's less of those up there. And they range from all over the world: Singapore, America, Cambridge. Our attorneys are American as well. So there's plenty, and of course local ones as well, Northumbria, Newcastle. I was in Durham last week, so you know, we get about quite a lot. The device A, as it's labelled, is actually used commercially at the moment. It goes into a deodorant product that is about to be launched. However, for us, it actually just lyses cells. So you pass your blood through it, and essentially it sprays the blood out the other side. It's instantaneous, which is very good if you want to do a handheld device that will diagnose it in front of the patient. The centrifuge on the right, B, is actually a design from a company in Leicester, and they sent a probe to Mars to look for DNA in soil. They're generally engineers, but for us, we shrink it down, we put it into a cartridge, it becomes a microcentrifuge, and it's very, very useful for us. If you actually want to see the whole process in action, if we click on the video, this is quite a long video, and I may not go through it all, but essentially this is it doing it. Now for us, this is a problem. You know, you don't want DNA and cellular debris flying around all over the place, and so you need to encapsulate that, but it gives you an idea of just how quick you can actually lyse cells and get DNA or all of the cellular debris out. This is a blood sample, so we've encapsulated this here. This device here has multiple different components in it, some of which we've made, some of which we've collaborated on. So the casings here are all from company in Cambridge. And what we're doing at the moment is lysing the blood cells. It's collecting in the bottom, and very shortly the pump will activate and the blood will disappear. Now, if this is the right video, it should happen at the right time. If it's the wrong video, it will take a little bit longer. But the whole process from start to finish at the moment takes around 13.5 minutes. So you're not quite at at doctor's appointment times yet, but you're getting close to it. So it's a very, very quick process. There it goes. And finally, it's disappeared through. One of the main issues, and the reason why this takes such a long period of time at the moment, or what we consider a long period of time, is the fact that it's got a lot of tubing between it. So at the moment, we're going from technologies that work to products that people can use. So taking these technologies and piecing them together so that they can be used in different industries. So anything that's biological and you want DNA from is a potential market. We concentrate mainly on medical. So at the moment, what we're seeing here, the discoloration is an extraction filter that we work on with a German company. And essentially what this is doing is it's binding all of the other cellular debris, and the DNA flows through it. It takes about 3 minutes. This little device here that looks like a stack of dimes, if you're in America, a stack of 20p pieces if you're here, is our PCR machine. Now, normally PCR would take you about an hour, depending on what PCR product you're looking for. This takes about 3.5 minutes, and what it's doing at the moment is it's whizzing around the outside of heated cylinders. And what this allows us to do, and you can probably just about make it out, it's about halfway up at the moment. What that allows us to do is take a DNA product and amplify it up very, very quickly. This is actually the nanowire sensors that we've been working on with Harvard and Yale, and at the moment we are sampling 64 different sets of wires, each of which can be individually modified to look for certain DNA targets. So if you had 20 different sexually transmitted infections that you wanted to test for in a single sample instantaneously while the patient sits in front of you, you're able to get an instantaneous readout of all of the different disease areas there. And we're working with a hospital in London in this area at the moment. But it's a very nice illustration of where you take lots of different technologies and different technology areas and bring them all together for a common cause, if you like, which is handheld diagnostics. So if we click off this, hopefully. Yeah, so the extraction, we worked with an institute in Singapore that were looking at some of the problems we had. So a lot of it's problem solving. The design itself of how you set up the filter caused problems with back pressures. Back pressures then blew the pumps and the gaskets, and you end up with nothing. However, changing the design slightly means that you extract a lot of DNA. The combination of the two, we believe now, is twice as good as, or you get twice as much DNA out as you would with the gold standard that's on the market at the moment. Science is, always changing. Being able to do a PCR in 3 minutes is, arguably probably the fastest you can do it in the world, we think. We haven't met anyone that can do it quicker. But you need to understand a lot about the fluid flow dynamics, heat capacities, changing of heats, and our ramp speeds are about 128 degrees a second as it flows around. But there's a lot of work that goes in behind all of this. The sensors themselves, the sensors are CMOS sensors, so they are incredibly similar to all of the chips that are in your mobile phones. The only difference is you tend not to get your phones wet, whereas the whole point of what we're doing is to flow fluids across the sensor, and that comes with its own challenges as well. So we have to collaborate with a lot of people, which all have slightly different niches. The software that goes into these devices is actually the same software that would be in a Toyota or a Mercedes or a Porsche. They're a UK company based down in Trowbridge, and it is essentially bulletproof software. You don't want your car brakes to fail at any time because your software blue screens on you. And the same is true with medical devices. So you need this type of this type of approach. So you go out, you find the software, you get them to develop it for you, and from there you end up with a medical product that can be approved by the regulatory authorities. What does it look like in its early stages? It's pretty ugly, to be honest. You know, it's got a lot of boxes, a lot of wires, a lot of tubing. But then you have to work with people that will take these types of technologies and design you products that will actually sell. And what sells will be different for different industries. A doctor will want one thing, a food specialist will want another, a police officer will want another, a forensic lab will want a different product again. Same technologies, different markets, different products. So the test bed, it's real, it works. And these are actual images. They are photos, they're not CAD drawings, even though that tells you something about how good CAD drawings are getting these days. And we're getting to the point now where we have a fluid base and a electronics base, and the next step is to push these two in together. That's it, it's real. But in the spirit of collaboration and open innovation, we worked with Harvard, and there was a talk earlier on IP. The importance of IP in this industry is absolutely massive, but it's also a very costly part of the work, but at the same time, it presents opportunities. So this was some work that was done in Harvard, comparing nanowires, nanopores together. Now, we licensed a lot of the work on nanowires out of Harvard, and we now work with Yale as well. Now, traditionally, that would be like Unilever and P&G working together. It doesn't happen very often. But Yale approached Harvard in order to get freedom to operate, in order to spin out a company to do this. And when they did this, they said, well, actually, a small company in the north of the UK owned the rights to this. So Yale approached us, and we were rather interested, and now our company and Yale work together, and also the spin-out company work together. So IP can be used in many ways, and so long as people are open to working collaboratively, then you end up pushing things forward. The sequencing part of what we do moves forward. So what we ultimately want to do is take an entire chromosome, stretch it out to its full length, and sequence the entire thing over all of our wires, so taking readings every, well, fraction of seconds, but essentially taking readings from 1,000 different sensors all at the same time across an entire chromosome. This is a piece of DNA, a whole chromosome that's been stretched out to 98% of its length, and we work with these guys in order to do it. And then we'll take this piece of DNA and we'll flow it across our sensors on our nanochannels in order to sequence the entire thing. That's a little way off at the moment. That's some data that shows the difference between nanopore sequencing and nanowire sequencing, and that's why we believe it better. Now, Quantum is a group of companies. Everything I've told you at the moment, up till now, is about QuantuMDx. However, innovation comes about from different situations, and Northgene is a company that's been in the Northeast for 17 years. It's been providing paternity testing, identity testing, immigration services for an awful long period of time. Based in the same place, Quantum needed more expertise in quality systems. They have quality experts. We started working together in that area. In the end, last November, we ended up purchasing the company. But Northgene's always been collaborative. It's always worked with people. It was spun out of the NHS and Newcastle University. It worked with LGC, who do the majority of it, and LGC is now a private company that do a lot of forensics. We acquired it. We gave it a dedicated laboratory and moved it essentially out of the NHS fold and the university fold. And we worked with a company in Warwickshire in order to essentially get the company to a point at which it could be accredited. And it was accredited last month. And now we're moving into new areas with this company as well. So moving into drug and alcohol testing, moving into forensics, and ultimately into toxicology. But the collaboration here is more than just staff being technically gifted and crossing over. Northgene will allow us essentially to take what we do in quantum and pull it through a testing laboratory so that we can actually provide our own data to support the work that we're doing, and then ultimately push it out into the market through it. So that's where we're at. And thank you very much for listening.